Okay, let's dive right into this explainer. We're exploring a fundamental truth of modern software today. Search isn't just a simple feature anymore. It is quite literally the hidden backbone of almost every single product you use. Think about it for a second. Whether you open a marketplace, an internal HR tool, or a documentation portal, you are immediately interacting with a search box, a filter, or an autocomplete. Because search is the substrate that everything else sits on, when it breaks, your entire product looks broken. Dashboards stop loading, widgets time out, and users, they don't blame search, they blame your app. So today, we're going to demystify how engineers actually tame search at scale.
Here's our game plan. We'll start by looking at the day zero trap. Then, we'll build a multi-region architecture, conquer the hot shard killer, implement smart routing, tackle real-world operations, and finally, wrap it all up with a scaling mental model.
All right, let's jump into section 1, the day zero trap. Simple until it completely breaks.
So almost every company starts out with what we call a day zero architecture. It's pretty straightforward. You've got a monolith serving user traffic, an indexer pushing updates, and a single Elasticsearch cluster. The code is all living happily in one place, and honestly, this simple setup works beautifully for the first 6 to 18 months. But the catch is it has absolutely no separation of concerns, zero isolation, and no graceful degradation. It's exactly like a single-lane road into a bustling city. Super efficient when traffic is light, right? But the absolute second a truck breaks down or rush hour hits, the whole thing grinds to a complete, disastrous halt.
And that brings us to the trap. Eventually, you're going to smash right into these 6 very concrete operational failures that crush every search team. A massive customer onboards, and suddenly your cluster costs just absolutely balloon out of control. A noisy query pattern hits, and because you don't have any rate limiting, your autocomplete latency spikes. When that cluster inevitably goes red, recovery is brutal. You're stuck doing deep Java virtual machine tuning, tweaking the core memory management of the system just to get back online. You basically hit a scale ceiling where you can't even experiment with new ranking models without risking taking down the entire live cluster.
So before we can design a fix for all this, we really need to adopt a principal engineer's mindset. For every single new component you add to a system, you have to ask 3 questions, in this exact order. How will it fail? How will we know it failed? And how do we roll it back? Seriously, if your system design cannot cleanly answer those 3 things, it is simply not ready for production.
Moving right along to section 2, the multi-region architecture, where we start building actual separation of concerns. To build a truly production-grade architecture, you have to split the system into 2 distinct halves, the write path and the read path. On the right side, we drop in a durable log, something like Kafka, to act as a secure waiting room for our incoming data, and we keep our backup cluster actively ingesting that data instead of just letting it sit cold. Then over on the read side, user requests come through a search API gateway that handles rate limiting, they pass through an isolated search service, and finally hit a relevant service for ranking. By putting up a hard wall between the durable write path and this highly controlled read path, we guarantee that a massive spike in back-end indexing won't accidentally take down your user's live search experience. Now here is where the real magic happens, the failover timeline. Because we kept that backup cluster active and ingesting real-time data, a complete region failure isn't a catastrophic multi-hour data restore anymore, it's just a simple routing change. The global router detects the latency degradation in a mere 50 milliseconds. By 100 milliseconds, traffic is transparently shifted over to the active backup. A user sitting in Singapore literally won't even notice that your Virginia cluster just went offline.
But wait a second. This introduces a super fascinating operational blind spot. The read your writes trap. Imagine an admin updates a document in region A, but their next immediate search query gets globally routed to region B, where that write hasn't actually landed yet. They see stale data, panic, and immediately file an angry bug report. Because active backups still take a second or 2 to sync, you absolutely have to implement mitigations here. Think session pinning, which forces a user's reads to the same region as their recent writes or write through caches. If you just ignore this, you are effectively running a latent bug factory.
Okay. On to section 3, the hot shard killer. Time to master multi-tenant scaling.
So real-world multi-tenant systems, they do not have perfectly uniform, equally sized users. They follow a brutal power law distribution. Tenant A might be a massive enterprise taking up 90% of your data, while the rest are just tiny startups.
If you naively route that massive tenant to a single database shard, that one specific shard gets absolutely crushed, handling all the disk, CPU, and query load for that giant customer, while the rest of your cluster just sits there totally empty. This is the dreaded hot shard problem.
And this leaves engineers totally stuck between a rock and a hard place. If you just use Elasticsearch's default behavior, which hashes by document ID, you get the fan-out problem. Since its tenant's documents are sprinkled evenly everywhere, every single query has to search every single shard in the entire cluster. It absolutely kills your latency. But if you try to fix this by hashing by tenant ID instead, you trigger the hot shard problem we just talked about, dumping 10 million documents onto one poor, overwhelmed node. Both of these naive approaches will completely fail at scale.
Which brings us to Section 4, Smart Routing, becoming aware of tenant sizes. The actual solution relies on a built-in Elasticsearch feature called the routing key. Think of it basically as a cheat code. It's a value you pass in your application code that overrides the default document hashing, ensuring that documents and queries sharing the same key are forced onto exactly one specific shard. By computing this key ourselves, we get to dictate exactly where data lives without needing to build any complex, custom proxy infrastructure. The best way to wrap your head around this tenant size-aware strategy is to imagine Elasticsearch as a 10-story hotel. Small tenants are like solo travelers. We bucket a bunch of them together to share a single floor, or shard, so we don't waste any space. But massive tenants? They're like huge families. We spread them across a bounded number of dedicated floors. They get the space they need to spread out, and when we have to find them, the front desk knows exactly which specific floors to check rather than knocking on every single door in the entire building. It's an absolute game changer.
In practice, it works like this. Small tenants query exactly one shared shard. Massive tenants fan out, but only to their dedicated bounds. This strategy is beautiful because it gives your big tenants horizontal scalability. It isolates them so they don't become noisy neighbors to the little guys, and honestly, it keeps your application code totally straightforward and operationally simple.
Let's hit Section 5, Real-World Ops, how to actually survive a Friday afternoon outage.
Look, an architecture only earns the title production ready when it survives the unglamorous realities of a live outage. You have to build walls to protect the system. I'm talking gateway rate limits so one rogue user doesn't hog the whole cluster, and indexer concurrency throttling so background tasks don't tank your live searches. And observability is completely non-negotiable. You need granular metrics like per-shard load tracking and Kafka consumer lag alerts. Without these strict limits in place, your single noisiest tenant is going to dictate the capacity of your entire cluster.
This brings us to the core principle of graceful degradation in action. A system has to degrade in tiers. It can't just completely collapse. Is your fancy ML relevant service down? No problem. Fall back to basic native Elastic skewered scoring. Identity service running slow? Cache the validation for 60 seconds. A system should always try to return something useful. Because in the real world, an empty or less personalized result is vastly superior to slapping your user in the face with a 500 server error.
Finally, Section 6, the scaling mental model. Let's synthesize all of this into a unified framework.
You can map out exactly what level of complexity your business actually needs by following this simple 5-step decision tree. First, profile your tenant sizes on a log scale to see if you even have a multi-tenant routing problem. Second, identify your read patterns. Third, audit your failure tolerance, like could you survive a region outage right now? Fourth, only add architectural layers when they truly earn their keep. And fifth, make it observable from day one. Because trust me, the instrumentation you don't build today is exactly what you'll be desperately wishing you had during your next outage.
This quote really summarizes the deepest lesson of today's explainer, and it applies far beyond just search. Scaling a system is the act of carefully adding the right boundaries between components so that failure in one place does not propagate to every other place. Whether we're talking about a routing key, an API gateway, an active backup, or a simple rate limit, literally every concept we've explored today is fundamentally just a boundary engineered to contain failure.
So I'll leave you with this to chew on. Have you purposefully designed the right boundaries into your own system, or are you just sitting there waiting for your next hot shard to take down your entire product? I hope this explainer gave you some practical tools to level up your day zero architecture and leaves you curious about how you can better isolate failures in your own engineering projects. Catch you next time.